Okay, thank you very much for the introduction. Let me confirm that everyone can see the slides here and also online. If it's not the case, please send a message as soon as possible. So today's topic will be about artificial intelligence, and we're going to talk about AI in music production, music information retrieval, which is various tasks in related to computers and music. And I will also try to talk about the ways AI can be thought as a source of creativity and provide new creative tools. And we will also talk a bit about like the downside of AI, maybe like what are the fears that people can have about it, even though I'm not an expert on that topic. And a bit later on, we will focus on two technical tasks in music information retrieval, transcription and tone transfer. And I will detail how these work in terms of AI architecture, the training process, and the people behind it, and how it works. So we can understand better also the mechanics of what we call AI in this context. So I think I have to start by talking about generative AI. So I think everyone in the audience probably has heard at least of generative AI. So at least people have heard of ChatGPT, and maybe in France we have this chatbot called Le Chat. So generative AI is this kind of system where you generate a large amount of text or images from mainly from prompting, from a couple sentences that you ask a question or a task. And it has become more than state of the art. It's become really like ubiquitous for these tasks. Maybe you've heard of Sora, for instance, for image generation. In this talk, I generated a few images using Crayon, which is a lightweight AI tool for generating images. For instance, here I typed music and AI, and Crayon provided like a couple images that you can see. They are weird-ish, but also kind of funny. And already you have some idea that you can make artistic content in a sense that with AI, it's not it's looking nice, and it's these images, they are not found on the web in other places, and they have some funny thing to it. So this is like the general picture for general AI. I'm not going to talk too much about generative AI because I don't want to focus on this aspect of AI, which I think we hear about too much, and is also not always the main tool for artists. But I think I have to talk about it. So let's see what we have for generative AI in music. So let's say, what are the tools we have to generate audio from a couple of words or sentences, and how they work today in 2025. When I first made this conference, which is about mediation, right? So I will not go too much into the details, but still, it was last year, and so I had a couple examples from what is called the Music Gen by Meta AI. So this is a work that was published in a national conference, where they basically explain how you can take a text input. For instance, I want a pop dance track with catchy melody, tropical percussion, and upbeat rhythms. And Music Gen will, from this prompt, generate raw audio that you can listen to and process, etc. So I just want to play that, and we can all judge the quality of this thing. So of course, my computer sound is really bad, and through my computer's microphone onto your computer headphones, it's probably even worse. But I would say, with a good pair of headphones or a good sound system, we can still hear that in 2024, this kind of generation, it was good quality and it respects the prompt. It's maybe amazing if you've never heard generative music AI before, because it is some kind of music and it respects codes of pop music with drums, and there's progression in the chords and they make sense, etc. But I would say it was not yet very realistic music. And this was an academic work, right, by Facebook. Some things we could also do with generative AI in music is modify an input melody. You would sing some melody like this one. Not sing, but play on the organ. Okay. And you would have the neural network here in that case modify the input melody into another audio file according to what you ask in the prompt. For instance, I want an energetic hip-hop music piece. So yeah, it's doing what you asked it for. It's analyzing the input pitch and rhythm and modifying the timbre of the instruments and putting some drum beats on top of it, which matches the. So it's doing a lot of things that you would consider human behavior, right? Musical behavior. The music quality at the end is maybe not great, but the core elements are already there. So quite interesting, I would say. And there are a bunch of models that are competitive with this one that are all published, and you can look at the source code and download the models and run it locally. Okay. But that was 2024, and so 2025 is another dimension in generative AI, maybe, and especially in music. And so maybe I would say in 2025, the main difference is that industry has taken over. So the one we saw before was Facebook research, and also Google research was one of the competitors. So it's still industry, but on the research side of things. Now we have startups or companies that do not publish anything about the research, but produce, let's say, they have products that people can use that are really efficient at doing what I just showed you, but better. So for the sake of argument, I created an account on this private company platform called Suno. I don't want to advertise it. I just want to show what we can do in 2025. There are other platforms. And so I recorded myself singing.
This is a song about audio AI. This is a song about audio AI.
Right. So I did that a couple of days ago and asked the tool to generate a song that has a K-pop style and house. And if you were there a bit earlier when I was testing the sound, you will have heard that. You see there's a progression, there's like an introduction, then the instruments come into play, and later on there is a harmonization of the singing voice. So again, very musical concepts. And another interesting thing for me is that the lyrics I invented when I sang were analyzed by the product, by Suno AI. And they understood the words. It was transformed, and my voice was regenerated into a new voice, which was pitched, and the tonal quality of my voice was modified. The instruments matched my singing pace, and all that was made into a song that is arranged with a progression, an introduction. So it's all these concepts from music production and composition that are known to this AI tool, which is, I think, is a new thing in the recent developments and is going to be probably even better and better in the coming months, maybe. So yeah, it's really good on the vocal part, I would say. Maybe the instruments behind are okay, but and yeah, and what is Suno doing at the moment is trying to give the artist, meaning me in that case, the creator, more and more control on what we can do with this tool. So to conclude on this generative AI thing that I have to address before talking about other tools, because everyone is wondering about these things, right? I just wanted to have a quick discussion also with the people here in the room, but also online about the big question, which is generative AI going to boost creativity because it lowers the technical barrier to start making music? Because more people, maybe like myself, can start creating music just with a prompt, and you can have fun with it. You can arrange the songs. You can try to make different styles of music that you don't really know how to play, but you want to hear it. And if you are a musician, you can also use this kind of tools to generate new ideas. And you can work with the AI tool. You can generate some audio samples, but work on them, and we'll see how artists do that right after this slide. Maybe there are other positive points that I'm not seeing, but for me, this can be seen as a good thing. Of course, there is a lot of interrogations about this technology. I think one of the main problems, in my opinion, is that the copyright laws and the general infrastructure of the regulation about these tools is not so clear at the moment. All these companies, including Suno that I represented, are under lawsuits for copyright infringement by the major labels, because you can guess that to get this kind of fidelity to pop music, you wouldn't have to train on arguably a large amount of data. But we don't know the training process because this is not published, so we cannot really know. And of course, people are afraid that producers and musicians will be replaced by AI. I'm putting a question mark here because I think it's very prospective and I don't really know how to talk about it. So maybe some people will have fewer jobs because you can generate nice music with AI, but also more people can create music because of AI. And you can live as an artist by using these tools, and we will see some people are already experts in that and already make a living with making music with AI. So maybe it's just a transition to a new phase of music. I don't know. And I'm not an expert on AI ethics, but in the discussion after the presentation, we can go back to this point and talk it in more details, I think. So this is a large chunk of the presentation, but I don't want to talk too much about generative AI. There are many AI tools beside these tools, generative tools. And I also want to address the question that artists have already started to make music with AI. So I want to talk about that. I want to see what artists are doing, what some artists are doing with AI, what tools they are using, and how it made them do different music, and how this was useful. And I will also do a little bit of vulgarization, mediation about what is machine learning. Maybe this is more targeted toward a beginner audience in machine learning, so I will skip that a little bit, but still want to be clear on what we call machine learning. Okay. So a starting point for seeing what artists do with AI for me was to look at this competition on AI music production that happens since 2020 in the Netherlands. It's called the AI Song Contest. And it's really interesting. Every year there is maybe 40 participants and the jury of experts chooses finalists, and then they compete with their song, and there is a winner that is chosen for various reasons, including the amount of creativity that they had in the process, and also the tools they used, etc. And we'll focus on two different years. Year 2022, where the winner was an artist called Your Boy Hanoi, and we can hear his song. If it works properly. Here. The link is in the slide, so if you're interested, you can have a look. You can listen at the whole song later. And I can also make you listen to another song, and then we can talk about what is AI in these songs, what was generated by AI, what AI tools were used. Maybe while you listen to the song, you can think about it, try to guess which part of the song was generated by AI, or what was the kind of tools that were used to make this music. And so the second winner was Onda Corta, and they have this song called Sudamerica.
Pasión, fútbol en las venas, samba en el corazón. Es majestuoso, selva sin igual, un sueño tropical. Del Caribe al cono sur la diversidad florece. Culturas milenarias, el legado permanece. Incas, mayas, guaraníes, su historia prevalece en cada...
So typically what I do at this stage is I ask the question to the audience, what do you think was made by AI and what was not? Well, with this hybrid setup, I think it's a little bit difficult. So I will try and give you the answers I can hear sometimes. So no, the whole songs are not generated by AI. It was not like these two songs. They are not just some people who wrote a bunch of texts in Suno AI and made these songs. It's not like that. It's more complicated. Actually, maybe we can listen back to the first song, and I can pinpoint in the first song, there's this da, 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 da. Okay. And this bit is actually one of the core audio sample that was made using AI tools. But again, it was not generated by AI directly. It was something more subtle. It was using something, called tone transfer, and we will talk about it at the end of the presentation. Okay, so here is the answer. So actually, there are many tools used in these two songs. Some of it are generative AI, but not for what you would think. So, for instance, the lyrics can be generated by AI. Okay. So for the second song, Sudamerica, most of the lyrics and the words were output by the AI, but not directly like write me lyrics. It was more like what are typical words describing Sudamerica, and the AI would give a bunch of words, and that would be typically stereotypes of what people would think when they think South America. And they used these words that come up often in the AI answers to kind of build the story of their song. So it allowed them to make a song about stereotypes on South America, which I find interesting, using AI as a way to see what most people would think about South America. Again, in this second song, they used a lot of text to singing voice. So some of the singing voice was generated by, let's say, an AI tool, but more like a text to singing this text. Just one word to one sample singing that word, not a full song just in one click. In the first song, the drum pattern was generated by AI. So when I say pattern, it's not the sound, but it's which piece of the drum kit and when the kit plays. So more like a MIDI file, right? And then this pattern was placed in a virtual battery with actual sound samples, and it was used to generate the drum pattern of the first song. And also, generative AI was used to have ideas about arranging the songs, the energy, all these kind of things. So it's all very interesting, but there are other tools which I want to talk about. The first one, and which is the core tool, the core two tools, for the first song, the one by Hanoi Aboy, is pitch detection. So it's an AI tool that analyzes an audio sample and finds the pitch of so the note in French language that is played by the instrument at any time. We also call it sometimes a fundamental frequency estimator. It will tell you what note is played at what time. It's like having absolute pitch, but by a computer. So we use that to analyze some sound samples and then use this information in the second tool. And we will talk about these two tools in detail, which is why they are in green. Second tool being tone transfer. And it's a tool that takes an instrument and transforms it into another instrument. And I have a demo right after. There are many other tools that have been used. So for instance, stem separation, like having a full song and finding only the bass or only the drums. There's been some tools for mastering the song, so mixing the different levels of the instruments. Also text to texture, which is some weird tool that will generate sound of the rainforest if you input some name of birds, for instance, which they use in South America. You can hear it at some places. Yeah. And on the right side here, I have a list of all the actual name of the tools that were used. And it's just a small subsample. Just to give you an idea that these people, these artists using AI, they already have a mastery of the tools out there, and they can combine all these tools and all these what these companies are doing and turn them into an actual song, which is, I think, great and a very creative process. Okay, so sorry, just to make a transition. So now, in the rest of the presentation, I will talk more about these two specific tools, pitch detection and tone transfer, just to understand what the AI tool is, how it works, what are the challenges in these two specific problems, and yeah, just to have more meat to chew when we talk about these things. So as I said, automatic pitch detection or recognition is the task to transform an audio, like, it doesn't work. So to go from this audio to, let's say, an informatic equivalent of this music sheet on the right, which we call MIDI. It's a file that contains the pitch information, so how high or low the note is, and the temporal information when the note is played. And we will describe one tool called Basic Pitch, which is open source and published work about this problem. And I'll make a little demo afterwards. The other problem and tool that we're going to study is tone transfer. And there's a nice demo about it by Magenta, which is the Google Music AI Research Group, or used to be. And this problem is, as I said, to go from one instrument to another by preserving the melodic line. So we can, for instance, have some birds. And have a saxophone play this thing. Or just the pots and pans on the violin. So I don't think you could hear it very well on with the video conference, but you can go and check the website. It's easy to find. And go and listen while I'm speaking. It's okay. To me, this tool is a very interesting tool because it allows to play an instrument you don't know how to play, and you can hear, if you listen carefully to saxophone, for instance, you can hear the keys being played. It's very precise in the timbre and and we will see how this one works in particular. So the roadmap to explaining these two AI tools, so the basic pitch transcription tool and the tone transfer tool, is this. I'm going to talk about machine learning concepts very broadly, and I will probably go a little bit fast because I want to spend more time on the rest. And then I will just dive into these two tools. I hope everything is clear up to this point. Again, with the hybrid concept, not so easy to interact, but at the end, I hope we can. Okay, so if you are completely new to AI, this is like the bread and butter here. So I would say I've been using the AI word since the beginning of the presentation, but I must say I'm not a big fan of using the word AI, especially in science. It has several ambiguous meanings to me. I would rather talk about machine learning in this context. And so when I say machine learning, I mean use a computer to analyze data or to learn from data. And the two main type of machine learning paradigm, I would say, are supervised learning and unsupervised learning. And we are concerned more today about supervised learning. Supervised learning is this task where you are given a bunch of examples, for instance, a picture of a cat and a picture of a dog. And with each example, you know if it's a cat or a dog. You have what we call a label, so a small bit of text that describes the image here. And you ask the computer, knowing these images and what they are, can you tell me what this new image that I have, and I don't know what it is, can you tell me what it is? Is it a cat or a dog? Actually, very hard to tell here. And unsupervised learning would be the task where you only have the images and you want to assign to group them in some way or to say something about them, maybe say if it's cats or dogs just by looking at the pictures. Okay. So supervised learning, which we're interested in today, I would describe it as there are three main concepts or pillars to understand what is supervised learning. The first concept, is the training data. So as I mentioned, in supervised learning, you have these images and their labels. So training data is really just having this collection of images, or in the case of music later, sounds. And if you think about applied mathematics, data would just be a bunch of points somewhere in the 2D plane, for instance. And supervised learning is about maybe learning functions or predicting things. So we like to formalize that as you have this underlying function that generates your data, basically like a god somewhere that tells you, given this image, is it a cat or a dog? And the computer has to learn this behavior, has to learn how to imitate this oracle or god. And so the goal is to find this kind of curve here, knowing only the data points. To do that, the second pillar of supervised learning is to introduce a model. The most basic model that everybody maybe has heard of at some point is a linear model. So just put a fine function here, and we'll be performing linear regression in that case. And so the model is just saying, I want to approximate my curve here by a straight line, in the case of linear regression. And when you have a model, you have parameters that allow you to choose which line you are interested about. And these parameters here are in purple, A and B. And so the third stage of supervised learning is training. It's tuning these parameters to have your straight line approximate properly your function. Okay. This picture here is important because it allows you to understand how machine learning works, and so why you need data, and also the question that you always ask when you see a new model, like the ones we see later for transcription and tone transfer, is always what was the model, often what was the data, the input data, and so on. Less often we talk about the training because I don't care so much, but it's my research field, so I like to talk about it. Okay. Instantiating these machine learning ideas for classification. So what the task of saying if each image is a cat or a dog, your function here is this oracle that predicts from an image if it's a cat or a dog. Your model replaces this function and is trained on only a couple of images, and it outputs a prediction. For instance, it would say here the first image is a cat, the second one is a dog. And then you compare this prediction on the right with the actual ground truth. Allows you to see if you're doing a good job or not, and optimize the model parameters based on that. And when the model is trained, I have this color code that it's gray now, it's trained, it's made to approximate the function. Then you input new data and ask the model what is the image, and it will say cat. And in fact, here it's a dog. So it can be wrong. Okay. And to conclude on this topic, what is a neural network? Maybe if you're not so familiar with AI, you've heard of neural networks, but you're not so sure what it is. I'm not going to talk about the actual workings of neural networks, which is beyond the scope of a mediation talk, but you can understand basically what it does by thinking of networks as very generic, nonlinear models. So remember this straight line that we saw going through the data? Now imagine this is not a line, but a very complex shape, and the parameters of the model can be changed to make very complicated shapes, very generic. This is basically what are neural networks. Okay. So I will represent networks by these mechanical monkeys because, contrary to the name neural network, I don't think neural networks understand or have a biological interpretation. I mean, you can see neural networks as in relationship to how the brain works, but they are not brains, not actual brains. So for the general public, I like to emphasize that and just say these are tools like code in the computer, just a mechanical monkey doing something it's trained for. Okay. And so once a network is trained, you can reproduce more or less the oracle function that you want to reproduce. Okay. So now that we have this concept clear, the first thing we need to talk about for music is what is the typical data that we have in music. So what is the input of machine learning problems? So the most obvious things that you would think about is temporal data. So just when you have an audio recording at home, it's typically a temporal file, just a bunch of intensities across time. And this is a very valid input for machine learning. In this presentation and in many machine learning problems for music information retrieval, we like to use another presentation that's called a spectrogram. Maybe you haven't heard of it. It's basically a representation of all the frequencies played at each time instant. And I have a little demo for that. Hopefully it will work well with the remote setup. Okay. So spectrogram has this kind of representation where on the x-axis you can see time, and on the y-axis you see the different frequencies played at each time instant. So, for instance, if you draw by hand something in this time frequency plane, it's very annoying, but it's basically a pure frequency, one frequency, so maybe 400 something hertz here. Sure. Okay, so different frequencies and presented across time. Different instruments have different time frequency signatures. For instance, the harp here, when you play it, it has this kind of shape, and you can see the flute we played earlier. It's very different. The flute is more harmonic, we say. It's annoying, I cannot stop it. You can see the fundamental frequency is here on the bottom. The lowest frequency is the one that gives the name of the note, and all the other peaks, they are called the partials. They are harmonics, and they basically characterize the timbre of the instrument. So if you listen at different instruments, they play the same note. Sometimes you can play A4 on the flute or A4 on saxophone. They will have the same fundamental frequency, the same lowest bar, but the other partial frequencies, the ones we see maybe in this picture, the other bars, they will have different intensities And these different intensities, they characterize the shape of the audio that we hear. Okay. So this is the time frequency representation. It's ubiquitous in audio processing, not just AI audio, it's everywhere in audio, because it's a way to have an image of what we hear. And it fully characterizes the, well, more or less, the audio we hear. So this is what we will put as input to machine learning models. So the cats and dog images we saw earlier, that would be now spectrograms or sometimes just temporal audio. What is the labels or the outputs? Why? It's typically the notes we play. So then it depends on the applications, of course, but in, sorry, for pitch detection, the task of finding the fundamental frequency, we typically label each audio sample by the note that is played, like la, sol, fa, mi. We'll put text on that. So that's the output. And also often the output is itself another spectrogram that you want to target. Let's say in the cats and dogs example, you will have as input a cat and as output another cat. So the label is another cat, another image, but a bit different. And you would want maybe to modify the input image into this other one. And I see that time is already running short, but I will try to finish in 15 minutes by 3 p.m. So let's dive into the actual AI tools, not what we understand, a little bit about machine learning. So first, we'll talk about pitch detection. And so remember this, this tool I mentioned, for basic pitch. I think we can have a try. Sorry. Basic pitch, you would sing. For instance, I'm going to try and sing. La, 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 la. The tool is processing my audio, and it's supposed to output the various notes that I sung. So I don't think you can hear it on the for the remote participants, but it's doing an okay job here. It found the pitches I sang, and it's putting them in a discretized grid with the time signature, etc. So it's doing what it's supposed to do. How does it work? Oh, sorry, before seeing how it works, why is this task difficult in the first place? Because you could think, okay, it's just, it's an old question. Humans can analyze audio and find the pitches that are played. Why is it difficult? Well, it's more difficult than what I just showed when you have multi-pitch instruments like piano or guitar, because you can play several notes on them at the same time. And well, it's not so obvious when you have several notes at the same time. Remember we saw instruments, they have this fundamental frequency and partials. And so if you have several notes, these combs, they overlap. And so from the time frequency representation or from the audio signal, you need to find different combs overlapping, and it's a difficult math problem. There are other problems, like you need to handle the variations in timbre from actual recordings. The different recording conditions can change the way the samples sound, the instruments sound, and so you cannot just base yourself on a few recordings that you know of each note. Some instruments have pitch bend, like the voice, like ah. So it's hard to actually characterize the notes I just sang, and so on. And I have to mention that the most famous algorithm to perform this task is not based on AI. It's called the Yin algorithm. It was developed in IRCAM in 2002, and it works pretty well, except when you have several pitches, pitch bend, etc. Okay, so back to basic pitch, which is one of our AI tools to perform this task of pitch detection. So basic pitch it's a work by Rachel Bittner here on the left, who is a researcher at Spotify. She published this work at the ICAT conference in 2022, which is a conference about acoustics and AI and signal processing. So it's all published and the code is available. You can try this tool. You can download it and run it locally. Also, the tool I mentioned, the basic pitch, this one, it runs on your computer. It's pure JavaScript. So it doesn't send your audio to a server, which is why I like to present this one, because it's also private in a sense. It's on the navigator, but it's not on the web. Okay, in a way. It has web information, but the computation is local. So the main ideas for this tool is to decompose this problem of pitch detection into 3 different tasks. Okay. The first task is to detect only what we call onset, so only the attack of notes, when a note is played in the audio sample. And we will try to build, the model will try to output a spectrogram called the YO for onset that contains non-zero values only on the onset locations. Second idea is to try and build a model that detects if a note is being played. This is basically the task in itself, right? If we know when a note is played, well, we have performed the pitch detection. And the third task that is also relevant for this problem is to finally denoise the spectrogram. So there is a part of the model that will simply take the input audio spectrogram, the one we saw earlier, and try to make it simpler. And this makes the other 2 tasks easier. Okay. So the actual architecture of this AI tool, Basic Pitch, is like this. The input audio is transformed into a spectrogram. So we'll have this time frequency information. And then the model splits the processing into different branches. You have this first neural network I call denoiser, which goal is only to denoise the spectrogram. So it performs this kind of clean spectrogram. There is a bunch of zeros everywhere. It's very sparse, very clean. It's trained to do that. In parallel, there is another network that only tries to detect onsets, as I mentioned, so only has non-zero values where there is a note being played. And and this one will be used in conjunction with the third output, which is called YN here on the bottom. And this last output is the output of a third block of the network that detects note. So this is actual network doing the job we want, finding notes in the audio. But it works not on the raw data, but on the processed data, YP, that, remember, is the output from the denoiser. So this whole architecture is meant to be like a multi-arm tool. Take the audio, denoise it, find onsets. From the denoised data, find notes approximately, and use onsets and not detected in a post-processing stage, which is basically just a bunch of thresholding on the spectrograms to output the MIDI. Okay. So then it's just a matter of choosing the actual models here, precise models. For music, for experts, is a bunch of LSTMs and some CNNs and these kind of classical architectures. And for training, they have a bunch of MIDI data registered with samples, audio samples, and they run that. They train the networks on this kind of data for hours. It's actually not very expensive to train compared to, let's say, vision transformers. It's quite cheap because the network as well is very structured. It's not so big in terms of number of parameters. And so the whole thing is trained maybe in a couple of hours on a couple of GPUs. Very reasonable. Also very fast at inference time. So you saw when I used the tool here, I input several seconds of audio and it took a couple of seconds to process on my computer. So this is all very lightweight and cheap in data, which is interesting.
When you say it's convolutional, you mean on the audio signal or on the image?
On the spectrograms. So there is the spectrogram seen as an image. So you would have networks take a bunch of local parts of the spectrogram and process it. I would like to look at the research paper more carefully to see the exact architecture. So the question was for people, what is exactly convolutional in this architecture? And so my answer is that the convolutional part is here on the spectrogram. You have convolutional filters that take the input spectrogram, and it's actually important to have some form of shape invariant network with respect to the input because the audio size can change. So if you input 1 second or 10 seconds, you need to be invariant to that. So you have always some kind of architecture that has convolutional or shift invariant structure.
But when it's convolutional, it's also invariant translation.
Yeah, exactly. That's why it's not exactly convolutional in the case of images. And also something I wrote here, and I didn't talk about. The input is not exactly spectrogram. It's a spectrogram stacked with octaves. And so there's a local third dimension that contains non-local information, spatially speaking. This is why convolutional networks can work in this case. And so something I like about this work too is that the post-processing is interesting. You can tune this kind of thresholds on the output spectrogram here in YN that helps you prune some nodes or put more nodes in the output. I will let you play with this tool if you're interested. It's fun. And I want to talk more about the last tool. So the tone transfer. I will try to go a bit fast. Sorry.
It's quite annoying.
Yeah, and we don't have time for that. So Yaboy Hanoi, he won this competition about AI music. And the way he won this competition was by using this tone transfer tool. He played quite a rare instrument called the Finai. It's an instrument from Thai music, traditional Thai music. And the tuning of this instrument, it's not the traditional tuning of European instruments. You can see here on this graph, the pitches, they don't match the traditional pitches. They are wider. And this is really bad for all kind of Western style AI tool or even digital audio workstations, because they all work assuming traditional MIDI. So discretizing this kind of playing is really hard. So he still wanted to be able to play his Finai and then make it sound like a different instrument, as the tone transfer we saw earlier. So the way he did that was first by using an F0 tracking algorithm. So similar to what we saw with basic pitch. He used a different algorithm, but the idea is the same. Output the fundamental frequency played at all time. And so if you look at this graph here, it is the fundamental frequency that he plays in the audio example we heard at the beginning. Da, 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 da. With the trill here. Da, da, da. So he has an AI tool that finds this frequency and then uses that in the second stage with the tool tone transfer, which we're going to talk about. So the first tool we already talked about, it's pitch detection. So to understand tone transfer, you need to understand a similar concept called DDSP, differentiable digital signal processing. It was a groundbreaking work published in ICLR 2020 by Jesse Engel and Yaboy Hanoi. So this guy has AI music and is also a leading researcher in AI audio, which I find fascinating. He also recently made contributions to the Chinese ChatGPT version. So very impressive. And so this is a work that was done in Magenta, which is the Google AI research group on music. And the main idea of DDSP, just to summarize it in very simple words, is to have neural networks or AI tools play a synthesizer. So the way it works is that given some input by the user, some audio input, it's analyzed by a neural network. And the neural network then is put in front of a synthesizer, metaphorically speaking, and control the parameters of the synthesizer, like the attack of the notes, the shape of the oscillators, and so on. And playing with these keyboards, basically, he tried to reproduce the sound that he heard as an input. Kind of autoencoder process for more expert people, but where the decoder is constrained to be physically meaningful. It has to be a synthesizer. And this idea can be used for a wide variety of tasks, for derivation, for also for transcription. But here it was used for tone transfer. And so how does it work? As I mentioned, you start with the source audio samples. You track the fundamental frequency of these samples. So remember this graph we saw here. It's the output of the pitch tracking algorithm. You also have some idea of the overall power of the audio input that you have, if it's loud or not. And these two simple parameters, two-dimensional, they are fed into a small neural network, which itself, this mechanical monkey, tries to control a bunch of musical parameters, like harmonic distribution. So which are the small sinusoids that compose the signal that you want to output, their amplitude, these kind of things. And these parameters, they are typically like a big synthesizer. If you don't know about music and synthesizer, all this block here, which is fixed, it's a completely physical block, it's like putting in front of a network, in informatics term, a NOR keyboard. Okay. And so the whole training process is just tuning here the monkey to receive fundamental frequency, loudness, and play on the keyboard, change the settings, and try to match the input audio. And why would we do that? Well, if we do that, we have this monkey that only receives fundamental frequency and loudness, and it doesn't really care about the sound of the saxophone in the input stage. It cares about the sound of the saxophone in the output because it needs to reproduce this sound on training. But once it's trained, you can take a finai, for instance, this Thai instrument, play it, track its frequency, fundamental frequency and power, and have the neural network try and reproduce a sound but of the saxophone for what it was trained for. And this is how you do a tone transfer. You trick the network into trying to reproduce a saxophone sound that was used as input, but the input was not saxophone, it was a finai. Okay. Hope it was clear enough. And again, these kind of networks, they are quite small and very interesting for me because the physicality of the output is ensured because we are playing a synthesizer. So we cannot generate weird audio, or we can, of course, but weird audio controlled by the output of a synthesizer. This was used for a variety of tasks, but here it was used for tone transfer.
Is it all trainable from the right to the left? Or?
So what is trainable is the red part. It's the model. So it's only the network that controls the synthesizer and some reverberation.
So it means that the synthesizer itself has to be differentiable.
Exactly. That's why it's called differentiable digital processing. So sorry for people online because there are like 30 people. The question was what is trainable, and I answered that what is trainable is only the input control network somehow, so that controls the synthesizer. And so the very interesting question that was led then is it means that if you implement it in PyTorch, you need to have everything that is differentiable so that the output here, you can compute gradients with respect to this red block here. And I say yes, and that was the main contribution of these guys in this publication. So it was the principle of doing these things and also releasing PyTorch synthesizers. Hope it answers your question. Okay. And of course, it can be used for more than tone transfer, and it's been the starting point of hundreds of works. It's cited like tens of thousands of times. So this idea was very critical in modern AI music in general. With this, I'm reaching the end of the presentation. I have a couple of slides to conclude. The first slide I want to conclude with is that if we zoom out a bit, remember I started by saying there are many tools that creators use to perform AI audio. I presented two tools, so tone transfer and basic pitch. Mind that there are a wide variety of these guys out there, including stem separation from noises, for instance, Magenta Studio, which is a VST tool for digital audio workstation that has, for instance, this drum pattern AI that I mentioned at the beginning. We have this Suno AI that generates audio and you can have fun with, although it's ethically questionable. 11 Lab, which is a ethical, quote-unquote, company that has voice processing tools for singing voice, timbre modification of voice, lyrics generation, and this kind of thing. So many tools. It's a jungle out there. It's fascinating, but hard to keep up with. And some final thoughts from myself, more personal. Something I realized by preparing the presentation is that music AI used to be mainly driven by research. So for the last 10, 20 years, the music information retrieval community has led all this amazing research on machine learning for audio, all these spectrogram presentations, DDSP, and so on. But nowadays, in latest years, the tools have been getting better, maybe because also they are driven by industry. Because the goal of startups in this area is not to do good research, is to have customers. And so they want things that sound good, that are easy to use, which indeed makes the tools more usable for everyone, but comes with at the price that ethical questions are more and more present. And also we have some difficulties to understand precisely how the tools work. For instance, Suno doesn't publish its results, so we don't know exactly what they do. We know basically, but we don't know exactly what they do. There are still some research topics that are slightly out of reach for AI companies. I would say transcription, the one I mentioned with the basic pitch, it's still clunky. It still doesn't work really well. Audio to MIDI is what we call it, or basically it doesn't really work well, and it's still a research topic. I find interesting. Another comment maybe is that all these tools I presented are all stemming from research groups, yes, but also from big companies. So Spotify, Google, Magenta, which is a bit depressing for us researchers, but there are also very nice works being done in laboratories. It's all in collaboration. I just wanted to mention that I presented mostly company work. And last comment is that you saw this guy, Yaboy Hanoi. You can follow him on Instagram and on his website. He's really cool, and he's promoting Thai AI music, which I find interesting because all these generative AI and AI tools, they're really made mostly for Western commercial music, pop music mainly. So with simple harmonies, hyper compressed sound, equal temperament, and basically piano, guitar, bass, drums. If you're a Thai player, don't really find yourself in this box. And you can do AI thinking about these other communities, and it's really also enriching to think about these problems and work on them. And so this guy is doing that, and it's really interesting. Okay, so thank you for your attention, and I'll be happy to take questions also from the people online, and I hope you could hear and see everything well. I don't know how we do this. Can maybe open your mic, or people in the room can also ask questions. I will repeat them. And
yes, so maybe one question regarding. I think most of the outrage regarding Suno is about what they are learning on.
Mm-hmm.
I mean, regarding all the copyright issue and so on. And so maybe, of course, there are some solution with just learning on not copyrighted material, or at least asking permission. But I think that regarding the fact that it may impact the business of artists, I think that the production material is not copyrighted, and it is not possible to copyright it, at least according to US law, but I'm not so sure. And so maybe it cannot really so deeply impact the business part for artists.
Yeah, exactly.
If a big company wants to monetize the production, they cannot use such tools.
So, did you hear? If you heard the question, can you say in the chat, because this way I don't have to repeat. The question was basically that. So, to summarize it in a few words, the legislation part is really a problem, and indeed, lawsuit is the main crispation point for Suno, but maybe for artists, it's not going to be the end of times, because the work that is done by using Suno is not copyrighted, and so you cannot monetize it in a way that would threaten artists. I'm trying to paraphrase. I actually agree with you. I'm not so clear. It's not so clear in my head what is the legislation about the output of Suno. I know you can put it on Spotify, for instance. And Spotify tolerates that, and we can monetize it this way.
I think if you pay for the pro version, there is a kind of copyright, but I don't know how it is, because it's not supposed to be copyrightable. So maybe the lyric can be copyrighted, but not the, I don't know. But I had this feeling that at least in the US, all IA generated material cannot be copyrighted, including images and so on. But
I think, yeah. So I will just answer. I think the legislation is not so clear. So I agree with the pro version. There is some part that you can use and monetize. And in Europe, I have no idea what they are doing about it at the moment. From my understanding, I'm not an expert in AI laws for audio. That's why. But my understanding is that it's all lagging behind. Basically, all these tools, Suno and competitors, they just appeared like 2 years ago, and they are starting to be used. So it's a bit of a blur line. But even with this, without this legislation talk, which I cannot really assess, I don't think artists are the ones that are the most afraid of AI. My understanding of it is that the music producers, so the big labels and that, they are more afraid because they are the ones that are caring about monetizing artists, and so they are the intellectual property of what is produced. I think for artists, maybe I'm a bit schematic here, of course, but they are mostly interested about producing interesting content and connecting with an audience. So AI cannot connect with an audience, so this part is more or less safe for now. And the part about creating new content, AI can actually help with that. So I'm trying to see the sunny side of the street, right? But
I think it's very hard to have a clear picture because
it's very hard.
If you look at comments on YouTube and so on,
Yeah.
Of course, you will just see it.
So, I agree. It's very hard to have a clear picture. I can also tell you what the big companies are saying. And so Suno and Spotify and all the streaming industry, they are saying these people who use generative AI as like a very simple tool. So not the ones we saw a bit later. So not these guys who are doing more expert stuff, which I find very fascinating. Let's say people who just use Suno and write a song and are happy about it and put it on Spotify. They are considered artists by these platforms, both by Suno and by Spotify, and they are giving them the tools to rise up as artists. So Suno is giving more and more opportunities to customize what its output. So rearrange the song, rewrite lyrics on the fly. Basically, they started to have this little digital audio workstation integrated into their interface, which I think is interesting because it's a bit like this old concept where, you had the cakes that you buy in the supermarket. And at some point, they only had powders and you put liquid and you had the cake. And people didn't buy them because they were too simple to make and was not really cooking. But the companies realized if they let people put the eggs in the mix, then people will buy and think they made the cake themselves. This concept has a name that I don't remember. But here it's a bit of the same. So the companies are trying to have people give more input and more feedback as users. And this way they feel like they are doing artistic work because they have more control. I don't know if it's good or bad. I think it's fascinating, but
I thought this might be why they can kind of copyright it, because I think what the US government went with is that it is about how much the human had control in it, and they decided that just giving a prompt is not enough control to make something copyrightable. But
right.
For example, just adding, I don't know, a pilot while writing a program does not prevent you from copywriting what you wrote, because you still had, you were in control and the AI helped you, and it was not the AI that was fully in control.
Exactly. So
maybe they also did that for it to be copyrightable.
Maybe. So the remark here is that copyright laws can also take into account this user input dimension, and the more input you have, the more debatable it is for legislation to say that the AI music created, for instance, was not an original creation, and so you can copyright it. I don't know. I'm not I don't endorse what they are doing. I just But I do agree with the fact that it's the more I see these tools being used, the more I believe that we're going to see a branch of music where AI is used at different degrees. And it's not 100%, not 0%. And it's exactly what this AI song contest is about. It's about using AI tools, all these different things for different tasks. But at the end of the day, the conductor is the human. And so I don't want to talk too much about copyright because I'm not
very similar discussions, I think, back to the 80s when something
yeah, exactly. For certain ties.
Issues were solved at the time. Yeah. What is the major term?
So yeah, the remark is that we had the same problem in the 80s with sampling, also in the 70s with synthesizers, also sampling became more of a thing in the 90s with the digital workstations. And so every time this comes up, and yeah, I think there's a scale difference maybe, like when you sample, it's obvious that you're going to remake and modify the song in a way. So they have this covered, and even then it's still a bit tricky. Like there are lawsuits on a regular basis, unrelated to AI, from one artist to another. For instance, because they think this artist used their baseline, or used their chord structure. And there has been successful lawsuits, I think by Katy Perry, for instance, on some other artists, because arguably some people said the other artist used her chord progression. But can you copyright a chord progression? I would say absolutely not. But apparently in some courts, in some countries, yes. So no, I don't think even without AI, the question is not completely clean cut, and it's evolving with society. But it's true that it's not. Yeah, and so I think maybe these questions of copyright are not only related to AI. That's why I'm not. I think you need a couple of experts in the room to talk about it. Yeah. Yeah, exactly.
I'm not here to defend Suno, but at least there are some things they are doing well. For example, I think it is not possible to, regarding the singing part, it is not possible to use the voice of an existing artist, or not even to ask to reproduce a style. For example, you cannot ask a music like the style of ABBA. And regarding other narrative IA tools, I mean, for example, for images, they are not so kind regarding artists.
Yeah.
So I think it was a good part, but maybe they already had a lot of, enough problem with the law.
Exactly.
So maybe they were soft on this part for now.
Yeah. So the remark in 2 words is that companies can modify their models to avoid some issues like copying artists or style of an artist. I think this is probably true. I'm not that expert on Suno, so you know better than me. But it's up to the company to decide to do that, which I find a bit scary because.
Well, there are the model of stable diffusion was not that bad, I think. They just have the website that any artist can access and opt out to not be in the database.
Yeah, I mean, it's
relatively easy.
Yeah, exactly. And some artists can actually enjoy being sampled this way. Yeah. So some artists can,
You have to have a process to be sure that the voice is your voice. So it's not so easy to do it properly. I mean, I don't know how with such a big amount of people using this platform, it would be very difficult to be sure that it is your voice and not the voice of somebody else.
Exactly. Exactly. That's why I meant by these companies are still private and a bit. It's hard to know what they are doing exactly. So they can communicate about these things and say you cannot use the voice of another artist exactly, but how do you make sure of that? How do you verify as an artist if your voice can be generated by the tool? These are actually research questions. And it's the same for other kind of problems like image generation or text generation. The same problem, the same lawsuits by.
But at least you cannot ask, I want the voice of one given artist.
Yeah, but for text, it's maybe easier. Like if you want to see if your article is generated by ChatGPT, you can prompt engineer and try to output the text. But for audio, it should always be a bit different, right? And mixed into a song. And so you need to isolate your singing voice from the audio, which is already a difficult task, even though some tools can do it. Then you need to analyze the audio and compare it to a similar recording of the same song and the same words, which you would do before the comparison. So you see, it's a bit harder, I think, for, I think personally, I think it's a bit harder. Probably it can be done, but it's not obvious how to do it properly and with some guarantees, statistical guarantees. And yeah, I realized we're only talking about generative AI, and my talk was not about generative AI, not too much. It's about also this other tool. So if you have questions about pitch detection or tone transfer or these musicians or this competition, I'm also happy to talk about it. Even though I know generative AI is the one asking more on the fire, let's say.
I have one about generative AI, but it's quite general actually. That if you look at what has been done in image generation, it seems that there is much more research support and also the open source community is much more active. For example, if you look at models like stable diffusion, which are open source, many people are using it. Also, there's the whole community that starts to like train small adapters for this model to specialize in some aspects. For example, you have like models you can plug to stable diffusion in like tractors.
Yes.
So there's a whole ecosystem of open source to the image domain. It seems that there is much less research support and also the open source community is much less involved on the music side. But at the end, it's pretty similar, right? It's another modality.
Yeah.
Do you know what is the reason?
So the question is, the audio community is a bit smaller than the image community, especially in open source and collaborative effort to reproduce big models and have a user, etc. I think it's true the community is smaller, but even rescaled to the size of this community, the vision community maybe has a more ancient history with older history for AI generation, and so maybe was more prepared to handle the big push of companies and neural networks and all that. Maybe some audio research lab was a bit surprised because nowadays to generate audio you use tokens, right? Yeah. And tokens come from text, from vision, and they take token of audio samples in time or in time frequency, which was not a concept at all in music information retrieval 5 years ago. So maybe we were collaboratively a bit surprised by the technology and we need more time to apprehend it. But still, I would say there are tools. By preparing this new presentation comparing to last year, I was searching on the web a little bit of on GitHub some repo where people have tools for generating audio that are open and collaborative. These tools exist. Okay, they are maybe not at the level of Suno or these kind of things, but they are there. You can contribute. It's more in the infant stage, and I don't. Yeah, the reason probably is, in my opinion, what I said. It's more. It's still a bit fresh, and the researcher in the community are maybe more lost. And also, these companies have hired most of the fresh blood in the community.
Do you think there is also like maybe a fundamental constraint on the available data? Because you need basically pair the data between the modality you're interested in and text.
Yeah.
And all images, for example, on the web are captioned or text or something.
That's true. It's true that the data is also an issue because for audio.
It's not, I mean, it is self-supervised or auto-supervised. So you don't need to have labeled data.
It depends on the task.
I mean, with transformers, it depends on how you are doing it. So I mean,
for text to image, you need.
Yes.
Yeah. Not labeled, but still auto-supervised, but you need at least to have a text.
Yeah. Yes. So we are having an expert discussion about neural nets, but so there is a part of the networks that are just embeddings from text or from audio to a presentation domain that allow also to do this music from melody to another melody, for instance. And this part has to be trained. I don't think it's self-supervised. I have to check. But so you need some amount of data at some point, and also just accessing a bunch of professional sounding music is probably harder than accessing a bunch of Wikipedia pages. It's doable for companies. For individual research labs, it requires a bit of. So typically in audio research, before like a couple of years ago, people worked on smaller databases, more controlled, and we didn't have like ImageNet for images or. So I do think data is an issue for public researchers in audio. It depends on the task, of course. Even just having the amount of data you need for self-supervised learning is good. Okay. Are there questions online? I'm sorry, the discussion is maybe not so easy to follow, but I see people are still here in the room. So. If you have more questions afterward, you can also send me an email. I will put the slides on my personal webpage. The link was sorry, here. You can find me on Google, just Jérémy Cohen research, and a bunch of people before me, and then you find me. Yeah, the slides will be there, and I'll be happy to answer questions afterwards. So thank you for attending, and yeah, hope it was interesting for you.
Thank you, everyone online. And maybe I can just thank again Jérémy, and just remind you that the next session of Journey Through Artificial Intelligence will be on the 25th of June about artificial intelligence and cybersecurity. Thank you very much. And the recording will be available online through the Arcus channels. Thank you very much, and see you soon.
Merci.